Hey, welcome. There's this hidden pattern that secretly runs, well, pretty much everything around us. It's this one shape that brings order to what looks like total chaos. And trust me, once you see it, you're going to start seeing it everywhere. All right, let's kick things off with a little puzzle. Think about this. What in the world do human heights, scores on a big exam, and even the tiny little mistakes a factory machine makes, what do they all have in common? I mean, on the surface, they seem totally random and unrelated, right? Well, let's dig in a little deeper. So first up, just think about physical traits. If you were to go out and measure the height or weight of thousands and thousands of people, you'd notice something interesting. Most people kind of cluster right around the average. You get very few people who are extremely short and very few who are extremely tall. And this pattern, it's not just physical. Nope, it goes for our minds too. Things like IQ scores. Well, they're actually designed to follow this exact same pattern. Most of us land near that average of 100, and the further you get from that score, higher or lower, the rarer it becomes. Okay, and this might be the most surprising one. Even random mistakes follow this rule. I'm serious. When scientists or even machines take the same measurement over and over again, the tiny little errors they make, they also cluster right around zero in this super predictable way. So what is this thing? What is this universal pattern? You've got our bodies, our minds, even our machines. All these completely different things are somehow connected by one single elegant mathematical shape. And there it is, the big reveal. The answer to the puzzle is the normal distribution. That's the official name for this incredibly powerful pattern that nature just seems to absolutely love. So let's get to know this shape a bit better, shall we? You've probably heard of it by its more famous nickname, the bell curve. And, it gets that name for a pretty obvious reason. It looks just like a bell. But what exactly is it? So, in simple terms, it's just a picture of how data is spread out. The very top of the bell, the peak, that's your average, the mean. That's where most of your data points are hanging out. And as you move away from that average to the left or the right, the curve slopes down, showing you that the extreme values are way, way less common. And here's the really cool part, the thing that makes this so elegant. This entire powerful shape, you can describe it completely with just two numbers. That's it. First, you've got the mean. That's the Greek letter mu, which is basically just the center of the bell, the peak. And second, you have the standard deviation, sigma, which tells you how wide or narrow, how spread out that bell is. Just those two things. Pretty wild, right? Now, this leads to this fantastic, super useful rule of thumb. In pretty much any normal distribution, about 68% of all your data, that's more than 2/3 of it, is going to fall within just one step or one standard deviation from the average. And it just builds from there. If you take 2 steps or 2 standard deviations away from that average on either side, you've now captured this huge chunk of your data, about 95% of it. And it's this predictability that makes the bell curve such an incredibly useful tool. Okay, so this all leads to a massive question. Why? Why does this one pattern so unbelievably common everywhere we look? Is it just some cosmic coincidence? Well, the answer is one of the most powerful ideas in all of statistics. This right here is the central limit theorem, or CLT for short, and this is the secret sauce behind the bell curve's magic. What it says is that if you take enough random samples from any population, and it really doesn't matter what the original data looks like, it could be totally chaotic, the averages of those samples will, almost like magic, start to form a perfect bell curve. And this shows you exactly how it works. You can think of the CLT as this great equalizer. See, when you start averaging a bunch of things, all the really high values and the really low values from your different samples, they just start to cancel each other out. Everything gets pulled toward the middle. And that's why something like human height, which is affected by a zillion different random genetic and environmental factors, ends up looking like this beautiful, orderly curve. So knowing this pattern exists is one thing, but how do we actually use it? Well, the bell curve also happens to be a kind of universal translator. It lets us compare things that seem totally different, like comparing apples and oranges, or in this case, test scores. To do this translating, we need a common frame of reference, and that's where the standard normal distribution comes in. Just think of it as the master bell curve. It's always centered at 0, and its standard deviation is always exactly 1.
So by converting any other bell curve into this standard format, we can suddenly compare them on a level playing field.
So here's the crucial idea. We can take a distribution like, say, GRE scores, which has an average of 500 and a standard deviation of 100, and we can translate any score from that system onto our standard curve. And the way we do that is with something called a z-score. It's just a simple way of saying how many standard deviations away from the average a data point is. I know, this can sound a little abstract, so let's make it real. Let's imagine you're applying for a really competitive scholarship, and the pressure is on. Okay, let's just walk through this. Your goal, score in the top 5%. So using our universal translator, we look up the z-score that cuts off the top 5%. That's the 95th percentile, and we find that value is 1.65. This just means your score needs to be 1.65 standard deviations above the average. Now we just convert that back. We take 1.65, multiply it by the GRE standard deviation of 100, and add that to the average of 500. And what do you get? You need a 665. Bam! We just translated a percentile into a real-world score. So, we've gone from a simple little puzzle to a really powerful statistical tool. Let's take a step back and just sum up why this one single curve is so incredibly important in so many different fields. So here's the big takeaway. The bell curve? It's not just some pretty shape. It's a powerful model for the predictable randomness that is literally all around us. We have the central limit theorem that explains why it shows up so often, and, most importantly, it's a practical, hands-on tool for making complex problems simple and for making some really powerful predictions. You know, whether it's managing risk on Wall Street, making sure products in a factory are just right, or figuring out if a new medicine works, this normal distribution is the fundamental lens we use to make sense of the world. So seriously, the next time you're just looking at a crowd of people or you see a bunch of data, ask yourself, hey, is there a bell curve hiding in there? Because now that you can see the pattern, what hidden order are you going to find?